we control for confounding. And there are essentially two groupings that we can think about. We can do it at the design stage, which is always preferential, or we can do it at the analysis stage, so once our data is in. And to do it at the design stage, our options are randomization, restriction, stratification, and matching. And we're going to unpack each of those in a moment. At the analysis stage, our options are to demonstrate comparability, stratification, and multivariable analysis. And again, we're going to unpack those in just a moment. Now, remember I said to you a few minutes ago that in order for something to be a confounder, it must be uneven between the two groups. Okay, and that is actually key to how a lot of this works. So let's start with what is essentially the gold standard for removing removing confounding, and that is randomization. And the really important thing that I do want to note first and foremost is that randomization refers to random allocation of an intervention, not random selection of subjects. Randomization is used to control for confounding in one and is only used in a randomized controlled trial. That is the key to them. Okay, and our aim with the randomization is to increase the likelihood that the distribution of exposure variables is the same for all groups. Okay, so the game there is to make everything balanced. So we would randomly allocate, and on average the age would be the same between the two groups, or we would hope to balance out the sex or the parity or whatever other factors that we may consider to be potential confounders. And the beauty of this technique is that it works for things that we know about, and it works for confounders that we don't know about, because the idea goes that if we've randomly allocated and we've done it well and we've achieved balance, then we will have achieved balance not just for those things that we can measure and know about today, but for things that may crop up in 10 years' time. And that's why randomized controlled trials, if done well, should stand the test of time. Now, the caveat to this is that we have no way, because this is an entirely chance approach of knowing going into a study how many must we include in each group to ensure that they are balanced. Okay, so that's the sticking point, and that's why when you see big randomized controlled trials in human medicine, you'll see thousands of subjects will have been included, and that's to ensure not that the sample size is big enough to detect, but that the confounders are balanced. And there is a lot of work that goes on behind the scenes analyzing in real time to see how they're going towards that goal. So just to sum up, because we've covered a lot there, randomization is what happens when we basically say we draw your name out of the hat and we decide whether you're getting a treatment or the control. Okay, and the process is one of balancing up confounders, and it works for those that we know and those that we don't know about, and it's the only method that works for both. Okay, the next method that can be used is one of restriction, and so that's really simple. It's we don't let a certain group in. So if we think that parity is going to be a confounder, then we may actually limit heifers. If we think sex is going to be a confounder, then we may limit it only to males or only to females. Now, it's a very powerful method because it removes confounding. It doesn't, for whatever you've limited it to, it doesn't impact on internal validity in any way, but it does have a hell of an impact on external validity, and it's something doesn't necessarily get talked about a heap in veterinary medicine, but certainly in sports science there's been a lot of discussion of late about the fact that a lot of the research studies done on performance have been done on male athletes, and they just don't transfer to females, and they were deliberately done on male athletes because they could prevent the confounding of female hormone fluctuations over a month. And so whilst those studies are incredibly valid internally when it relates to male athletes, they do not have the external validity to be applied to all athletes. So just something to remember with restriction. It's a very quick, easy way to do it, but it could limit who we apply the results to. Another approach we might use is stratified allocation, and we can do this in two ways. We can sort of do it in the sense of if we thought farm size, for example, was going to be a risk factor, we could randomly select similar numbers from small, medium and large farms, for example. But where you'll really see it come into play is in randomized controlled trials, where people will be stratified and then randomly allocated to a treatment or control. And the purpose of that is, remember I said that it's a chance whether or not you get a balance. And if your goal, obviously as it will be, is to ensure balance, and you've got a particularly important confounder, then it makes sense to get ahead of that and ensure balance from the design stage by stratified allocation. Okay, now the final thing that you can do is at the design stage is called matching. Now matching is actually a lot more complicated a technique than it sounds. I mean, it sort of seems easy. If my first animal to come in is a parity 1 animal, then I match it with an older parity. Okay. The problem is it only works for known confounders. It's also actually used for a variety of reasons in study design that have nothing to do with confounding. They have to do with optimizing and reducing sample size requirements and so forth. And the problem with it is you can't evaluate the matched factor as a risk factor. So if you match on something, you need to be really sure that it is that risk factor and that you're not going to want to explore its effects independent. Okay, so it's not a really good technique to use unless we really understand the problem we're investigating. You also, in terms of analysis, you don't need to do anything fancy if you've matched in a cohort or randomized controlled trial, but matching in a case control study in and of itself doesn't remove for confounding unless you use appropriate statistical techniques. So really key point, you'll often see in case control studies they might match on age, they might match on gender, and the idea that many people incorrectly come to is that that controls for the effects of age or gender. It doesn't. Okay, and unless you deal with it also at the analysis stage. Okay, we do delve into this more in one of our other papers, but I think it's just important to know that in case control studies, matching is not a solution to confounding. It only really works for cohort and randomized controlled trials. Okay, so when we get to the analysis stage, we have an options which are to demonstrate comparability. So what that would mean is that you would work out, if we go back to the is age a confounder of mammary cancers in a study that's looking at the effect of neutering, the way we would do that is we would demonstrate that on average the dogs that were neutered were the same age as the entire dogs. And you can try that. The reality is that it often doesn't get through review. It was something that used to be used when the statistical methods were a lot harder to apply. Now that they're easier to apply, the expectation is that you really will control for it. The other method, and this also is used very rarely today, is stratification. It's a simple statistical method in which you effectively stratify and calculate values over a couple of 2x2 tables instead of one. The calculations are pretty straightforward and can be done by hand. The downside is you really can only control for one confounder at a time. All right, so if you've got 3 or 4 confounders, stratification is not an answer. It used to exist because it was one of the few options we had available before we had the computing power. But now we do have the computing power, and one of the most common techniques we use to control for confounding are multivariable models. The great thing about them is that they run for a number of confounders simultaneously. It does involve us using software such as what you'll see in the methods are R, SAS, Data, incorrectly spelt there, sorry. And you'll also see a variety of statistical techniques. You might see multiple linear regression if the outcome was something continuous like average daily gain or weight. Often though, you'll see multiple logistic regression, and that's because that's an approach we can use when we have an outcome like disease, not diseased, case or control. Another method that you do see a lot in the veterinary literature is survival analysis, particularly around dairy herds and so forth. And it's just a technique that allows us to look at factors that affect the time until something happens. The reality is we do not expect you to know what all of these techniques are best used for, and in some extent you've really got to accept that the stats was okay, but you can use this little bit of knowledge to help unpack what was going on. And so we're going to talk now about reading a paper that used a multivariable model.